Okay, here's a gantry truss, and you can see it's been supported on the left hand side with a fixed pin joint, which means that the reaction at this pin joint will not be perpendicular necessarily, certainly not actually with this force acting on an angle, this 5 kilonewton force. And we've got a roller joint over here, meaning that we're going to get a reaction which is at right angles to the length of the truss. Okay, so we've been asked to work out what is the reaction at A and the force in the members CE and DE, those two. So first things to do this, and we're going to use the method of sections to work out the force in these two, but before we do that we've got to work out the reactions at A. Now I'm going to work out the reaction at B anyway, just to go through the process so that we can be clear on it. First I'm going to say that the reaction at A, I want to define it a little bit. I want to say that it's going to be a reaction like this. I'm guessing it's going to be that way, and it's going to make an angle theta with the horizontal, and it's going to have a horizontal component called RA cos theta, and it's going to have a vertical component called RA sin theta. So I've resolved those into horizontal and vertical components. Next thing I want to do is look at this force here. Now, rather than play around with this 5 kilonewton force and work out perpendicular distance when I take moments about points, I'm going to split it up already. So I know that angle is 45 degrees, I've been told this in the question. So I would fairly safely assume that we've got a force here which is acting there, which is going to be 5 kilonewtons sine of 45 degrees, and I have an additional force down here to resolve this 5 kilonewtons. 5 kilonewtons cos 45 degrees. Now they're going to be equal because of the geometry of this thing. I've worked out that 5 sine 45 degrees and 5 cos 45 degrees, because sine cos is the same, sine of 45 degrees is the same as cos 45 degrees. Worked out that we have that sine of 45 degrees is going to be equal to 3.53 kilonewtons, and so is cos, which makes it we're going to have a total force down here, which I'll use a red pen to indicate a total force coming down here of 8.53 kilonewton. So it's the sum of the 5 kilonewton force plus the vertical component of this 45 degrees 5 kilonewton force. So 8.53 here. We've got a force acting up through here. We've split it up into vertical and horizontal components. And we've got RB, which I haven't indicated yet, but there's RB. It's going to be vertically upwards because of the roller joint. Okay. Now to solve for RB, let's take the sum of the moments about point A, and we'll make it this way positive for argument's sake. And that we're going to get an 8 kilonewton force, so 8.53 kilonewton force multiplied by this distance here. We've told that's 2 meters, so it's 5 meters. And plus we've got some moments about A, this force acting downwards. We've got this force here, which is the horizontal component of that angular force that we had, the 5 kilonewtons. It's going to acting 1 meter away from the pivot point at A. So it's going to be acting in a anti-clockwise direction, so it's going to be minus. So 3.53 kilonewtons times 1 meter, because that's the depth of the truss down here. And lastly we've got minus RB multiplied by the full length of the truss, 10 meters. And all that equals 0 because it's an equilibrium, so some of the moments have to be in equilibrium. We can solve for that and say that RB, therefore RB, the reaction at B is going to equal to 3.825 kilonewtons acting vertically upwards, and that's just simple maths to work all that out. Alright, now let's take the sum of the moments, or let's do sum of the vertical forces, indicating this way positive, upwards being positive on the page. And we're going to get the component here, RA sine theta, well that will equal 0, so it'll be RA sine theta minus the 8.53 kilonewton force acting downwards, plus RB equals 0. And from that we can get that RA sine theta is going to equal to 8.53 kilonewtons minus RB, which we've already worked out to be 3.825. So that now then equals to 4.75 kilonewtons. So we've solved for the vertical component of that force. We'll call that equation 1. Now let's take the sum of the horizontal forces, this way positive. There's not many horizontal forces going on here, we just have this component here. It's positive because it's to the right, so it's RA cos theta, and we've got this component over here, which is 3.53. Oh, I beg your pardon, we should watch that. That's negative. Because it's pushing this way to the left, it's negative RA cos theta, positive 5 kilonewtons sine 45 degrees, which is there, which is 3.53 kilonewtons equals 0. So from that we can say that RA cos theta equals 3.53 kilonewtons. We'll call that equation 2. Okay, so dividing 1 by 2, 1 divided by 2 produces tan theta equals 8.53 kilonewtons divided by 3.53 kilonewtons. We've got rid of the RA, it simply disappears when we do the division. And from that we get theta equals 10 to the minus 1 of this result here, that division, which equals 50, just over 50 degrees, 50.66 degrees. And it's the correct direction because it's positive, so we've guessed it correctly. So it's going like that. So we've got the angle of the reaction. Now we need, at A, now we need to work out the reaction itself. So plugging this angle that we have over here back into equation 2, we're going to get that RA is going to equal to 3.53 kilonewtons, all divided by cos of 50.66 degrees, which means it equals to, not really doing it in my head, but I've worked it out already, it's 5.57 kilonewtons. It's positive, which means we've guessed the angle correctly. It's up that way, so there it is. So there's RA. So that's the first part of the question worked out, which is a reaction at A. Now the next part of the question deals with the method of joints, so we'll look at that. The method of joints relies on the fact that all parts of a truss will be in equilibrium, or any object will be in equilibrium, regardless of whether you slice it in any section. What it means is that if we slice it down in a section, or create a section through that truss, all the external forces will match all the internal forces in magnitude and be opposite in direction. So internal forces, if we take a slice, would then have to come into play to create balance. And I'm going to create a balance because I want to create a slice. We want CD and DE. So I'm going to take a slice down through here like this. And I'm going to redraw it down here for you so it looks a little bit more clear. So we're going to have a section of the truss going like that, another section coming down, going up here, going out there, and there's the section line that I've taken. Alright, now given all that, we're supported here at A. So we've got two forces, and I'm going to use horizontal and vertical components at A rather than trying to use that angled force, because when I come to taking moments, which I'm going to, horizontal and vertical forces make it a lot easier for me. So I know I've got a force acting here at A called RA cos theta from up there, and I know what RA cos theta is from my previous working. It's 3.53 kilonewtons. So I've got a 3.53 kilonewtons force here, and I've got a vertical force here which is RA sine theta, and I know that RA sine theta is flying around up here somewhere. RA sine theta, yeah, there it is over there, 4.75 kilonewtons. So it's 4.75 kilonewtons in the vertical. Alright, so I've got this section. Now I'm going to have to do something else. This is not going to be balanced without some opposing forces coming through these members that I've got here. I'm going to guess that the top member over here will be in compression, so therefore its internal forces will push away towards the joint. That's usually a compressive force. Now if I get this wrong, it's okay. The sense will indicate with a negative if it needs to be changed direction. But at the moment I'm going to guess that, and I'm going to guess that this too will also be in compression, and I'm going to guess that that force will be in tension. Now as I said, it doesn't matter which direction you choose the arrows to be. If you end up getting a negative result for one of these forces, it means that the arrow had to be in the opposite direction. So these are tension forces, and they're a reflection of the internal forces, which are pushing back outwards, resisting the compressive force pushing inwards. On the bottom chord of the truss here, the opposite is happening. This is an internal resistance force pushing inwards, resisting the outwards bend. And if you can imagine the truss, it's going to be bending, sagging in the middle. You would expect tension on the bottom and compression on the top of the truss. Okay, now if I extend these lines over here, so you can see the dotted lines, when I take my moments, and I'll label this according to the instructions. The real skill here in the method of sections is learning how to take moments in the right spot to save yourself time and effort. Now, when you do a slice, you should always try and slice no more than 3 members that you're not aware of in your slice. And when you take moments about that slice, try and make sure that you take moments about the joining section, the extension, where the two sections of two of the forces would, the point through which those two forces would flow, leaving the third force exposed for you to calculate. So my first moments are going to be a moment about D, because if I take a moment about D, I eliminate these two forces, I'm left with these, and in fact I don't have to worry about the horizontal force because that also goes through D. And I've got this vertical force here, which I know the distance because I've been given it before. It's 2 meters. That's part of the information that was given up here on earlier. Alright, so given all that, let's take moments about D, as we said. So some of the moments are about D, and we'll make it this way positive. So as long as we're consistent, it doesn't matter which way we take. So we're going to have, that's going to equal to CE, or force CE, times the perpendicular distance down here. And what is that distance? Well, if that's 2, and each of these sides, or that's 1 meter, because we're told that information's been given to us, that this is 1 meter and this 45 degrees, then the perpendicular distance from CE to D is 1 meter, so it's CE times 1 meter minus this force over here, which is 4.75 kilonewtons multiplied by this distance here, which is 2 meters. Okay, so it's easy enough to solve for CE. CE becomes 8.61 kilonewtons, and because it's positive, it means that I guessed the correct direction, meaning that the bottom member is in tension. If it was negative, I'd have to reverse it, the arrow, and say it was in compression. Okay, now next thing, I want to be able to solve for CD. So I need a place to take moments about, which would eliminate this, which I don't want to work out, AD, and eliminate AC. I don't need that. So really the obvious point is taking moments about A, and I'm just left with CE, which I know I've already worked out, and CD, which I want. So I'm going to take moments about A, and I make it this way positive again. So with that I get my CE force, which I already know to be 8.61 kilonewtons, multiplied by the perpendicular distance from A, that's this distance down here. Now by Pythagoras' triangle, this is 2, this is going to be, well, we already know that, times 1 meter, plus CD, this is where I'm going to need my Pythagoras, plus, okay, this CD, this distance here, multiplied by the perpendicular distance. Now that is a right angle, though it may not look so, because this is 45 degrees and that's 45 degrees. We know that from information given to us up here. So if that's 45 degrees, then that's a right angle. I only need to work out this distance here. And if that's 2, and this distance over here from A to C is going to equal to root 2. Okay. So what that means then is that we can now solve for CD, which is what we want. We find that CD is going to equal to 6.09 kilonewtons. And because it's positive, that all equals 0, by the way. Conditions for equilibrium, some of the vertical moments have to be 0. CD is going to equal to, one thing I forgot to mention is that CD is rotating around this way, making it, I had the direction rotating around that way. See the arrow pointing down here, which means that really CD here should be not minus, it should be minus CD. Minus CD, which of course means that the overall result for CD is positive, giving me the correct sense that I've chosen as being a compressive sense on this member. Yeah, sorry about that. Okay, that's sorted. So CD is 6.09 newtons. And that'll also be in compression. That'll be in compression. Okay, so there's your method of joints. Again, the thing to be aware of with the method of joints is to choose your sensors of your forces wisely and pick the moment where to take moments in such a way as to eliminate 2 of the forces and leave 1 force remaining, which you can easily solve for. I hope that was helpful for you.